Let's see, we've got Reagan now.
Like,
Hello. We've got Julian, Mohammed, Chase, Alex. We've got Bryce, Brian, Nicholas. Nathan, Dawson, Alex. We've got a great class. Okay, the topic for today is the change of entropy equations for ideal gases. But do you have any questions for me before we begin?
Professor, this is Nathan. I did have a quick question.
Sure.
On homework problem 650, this is an ideal gas problem. So, and you mentioned for that we are using equations, not tables. Am I correct?
Yes, yes. 650, Nathan?
Yeah, this is a homework problem. So I'm not asking
Okay,
you to do it. I just
let me find it here and see what we're talking about. 650 air. We're talking about air. And what about it, Nathan?
Well, I just want to make sure to find the to do the TS diagram to find the entropy, change in entropy. I'll be using I noticed that there was a table where you can find values for entropy for air, but you said not to use tables. So I was just a little bit confused about that. I know the equation.
Yeah, I'm going to try to clear that up for you guys today. And I might even just do that problem for you. That'd be all right. Nathan wants to know, he's a little bit confused there about it. But let's talk about these. There's two equations, Nathan. They go like this. And I want to show you where they come from. Brian. There's one that goes like that, and then there's one that goes like this. Of course, you'd have to plug in your limits there. I want to show you these equations, and I bet one of those equations is what you could use. Nathan was talking about problem 650. He wanted to plot a TS diagram, find the heat transfer. We'll come back to that, Nathan, but I want to talk about these equations and where did they come from. Now, it'd be nice to know what the final pressure was. Let me just talk about 650. Nathan's a little confused, I guess, and there's a PV diagram and there's a TS diagram. Let's look at both of them. Now, there's no vapor dome. We're talking about air here. So you don't put a vapor dome with air. It doesn't turn into a liquid. You don't have a solid or a liquid. It's just a gas, okay? 3 kilograms of air. Oh, it's constant. It's constant pressure, right? Keeping constant pressure. Well, here, Now this is going from 300 or no 27 Celsius to 500 K. This is 27 Celsius. Just a minute here. What's 27 plus 273? It's about 300, isn't it? Yeah, it's about 300. So you're starting off at roughly 300 K, and you're going to 500 K, and you're doing a constant pressure. Da, 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 there you go. From 1 to 2. Now on a TS diagram, it's constant pressure, but constant pressure lines kind of go like that. Now, what is this pressure? It's, well, we don't know, but we could find out. Look here. Oh, no, they gave it to us. It's 300 kilopascals. This is 300 kilopascals. This is the 300 kilopascal isobar. There it is. And we're going to go from 1 to 2. Here's 1. Here's 2. And here is 300 K. And here is 500 K. Am I helping you any now so far, Nathan?
Yeah, this is all fun.
And do you need any more help with that problem? I'll be glad to. Do you need any more help?
No, I don't need help with the diagrams. I just want a clarification on the equations is all.
Yeah.
Yeah.
Okay. Well, one last thing on the equations. Since it's an isobar, you get to use this equation here. And for air, this is equal to C sub P delta T. You can look that up. You know the delta T. You can find the little q. I think they want big Q, but see, big Q is just mass times little q. So I know you can do it.
Yes, thank you.
You are so very welcome. Now back to what I wanted to talk about. I wanted to talk about these equations and where did they come from? See, we could even do those with this problem here. You get the same answer on both. The change in entropy between 1 and 2 is the same no matter what equation you use. And see, you know everything in here. You know C sub P, and you know the temperatures, you know R, you know, hey, look at here. Those pressures are the same, so that's just a 1. The natural log of 1 is 0. So on this particular problem, that whole term drops out, you know it? And you could write the change in entropy by writing, well, we'll do a little s. Now, to be correct here, I do need an m in here. See that this is the equation for little s. If you wanted a big S, you'd have to have multiply by m. But see, we can pull out that C sub P. It's 1004 kilojoules per kilogram Kelvin. And when you integrate that, what you'll get is the natural log going from 300 to 500 and you get your change in specific entropy. It's going to be positive. See, here's your S1, and here's your S2. And you can get that change there. It'll be equal to I'm doing this on my calculator here. I got 0.5129. See, it's positive. It went to the right. The entropy got bigger.
Professor, so that,
Go ahead.
I'm sorry. Okay.
No, go ahead.
So that value you just came up with is basically the difference of subtracting the entropy value on those tables that we were talking about that I guess we're not
Yeah.
supposed to use. You
We're-
get that 0.5.
Let's do that with those tables, Nathan. Let me find them first. For air, I'm looking for them. They're called ideal gas integral tables. And they have 300K. I need a little room here. We need some room. I need some room. See, to get the Q, we need the delta H. In other words, we need H2 minus H1. Well, H2 at 500, according to these tables that Nathan has discovered, is 503.36. Kilojoule per kilogram Kelvin. And H1 at 300 is 300.47. Same units. Now, if you subtract those, what you'll get is 503.36 minus 300.47. You'll get a little Q of 202.8. Is that what you got, Nathan? Did you get 202?
Yes, I think so. Well,
Okay.
I think I got big Q, so I multiplied it by 3. So I think that's right. Maybe I'll do it.
Okay. Now, if you do it this way, here's what you'll get. You will get 1004 times, that's kilojoules per kilogram Kelvin, times 500 minus 300. Okay. And what you'll get is you get 200.8 kilojoules per kilogram is what you'll get from those tables. Now that's pretty dang close, Nathan, to 20, rounded off to 203. This is like 201. And actually, these are a little better. We'll put a happy face on those, but these are pretty darn good. We'll put kind of a little sort of satisfied look on those there. So what you did is okay. Did that help any?
Yeah, that's fine. Thank you.
Yeah, anytime. And notice that the change in specific entropy got bigger. It moved to the right. Look at, you're going to the right. There it is. Move to the right. So that's kind of interesting. Okay, now back to our topic. I wanted to talk about those ideal gas equations. Now, let's see if I can explain that. This is all in your book, of course. And let me make some room here. We'll kiss that goodbye for now. Now what we're trying to do is we're trying to come up with these equations here. I'll put them down here. This is going to be our end result. And there's another one down here. I'm too lazy to write it right now, but these are all in your book. But where these came from, they came from the Gibbs equations. And the way they go is like this. These are called the Gibbs equations. There's two of them. The other one goes like this. Once you got these Gibbs equations, then it's just a matter of some algebra and calculus, and bam-o, you've come up with these equations here. The other one goes like this. But where did they get these? Well, they got them from, actually, let's write them with little letters. I like the little letters better. There is no little p, but there is a little v, absolutely. And this one goes, there is no little t either, but there is a little s. See, this is entropy, and this is specific entropy. This is enthalpy, and this is specific enthalpy. This is volume, and that's specific volume. Those are your Gibbs equations written in little letters. Those equations are good whether you have an ideal gas or not. They're good for refrigerants, ammonia, water, you name it. They're good for anything. Now, where did they come from? Well, they came from the ideal gas law. I'm sorry, the first law of thermodynamics that we all know and love for control volume. So we're dealing with a control volume. We're dealing with a control volume, and we're going to write this in differential form. Now, you can't write it as an exact differential because that implies that you have a heat at a state 1 and a heat at a state 2. That's no such thing. Heat is a path-dependent quantity. It depends on the process. Work is the same way. You don't have work at some state 1 and work at some state 2. Work is a process-dependent thing. You have to have, it takes time to do work, and you have to go from one state to a different state through some kind of process in order to do work. So they don't have exact differentials. They have, this is just a small amount of stuff is what that delta means. It doesn't mean subtract anything. It just means you've got a small quantity of heat because you have your processes that you're going from state 1 to state 2 is a very small, it's not a vast process. It's a small process. This would be a small change in your specific internal energy, because going from state 1 to state 2, they'd be very close. It's not a big change. Okay. So what? We came up with a wonderful equation for the change in specific entropy. It was equal to this here. And we had to have a reversible process in order to get that. Can you read my writing? That's supposed to say d little s. And so t times d little s would equal your dq. Hey, we could substitute t ds for that little dq. Can you see it? Keep in mind now, it had to be a reversible process. Now on work, you guys all know work is integral of PdV. If you wrote this as just a small smidgen of work between two very close states, you could write this as P dV like that. See, to get from here to here, you take the integral. To get from here to here, it's taking the derivative. Okay, well, we could write that as negative P dV, couldn't we? So far, I hope you followed me. We're almost done. Now what we're going to do is a tiny bit of algebra. We're going to go TdS is equal to du minus P dV. Boy, Jove. No, wait a minute, I did that wrong. D plus, there you go. I did my algebra wrong. When you go TdS equals du, you have to go plus that on the other side. Hey, we just got our Gibbs equation, didn't we? We just got our Gibbs equation. There it is. Now I can show you from this Gibbs equation how to get to equation for entropy change. But first, let me go ahead and get the other Gibbs equation. This is the other Gibbs equation. Let's see if we can do that. Okay, well, I need a little room here. We're going to start with delta H. Let's do it this way. You know what H is. H is equal to U plus PV. By definition, that's a definition. So dH would equal to du plus P dV plus dPV. I used the product rule. You didn't get lost, I hope. Hope you didn't get lost. Now do some algebra and rewrite this as du equals dH minus PdV minus dPV. And what we're going to do is we're going to substitute that in here, and what you'll have is TdS is equal to dH minus PdV minus dPV plus PdV. Oh, looky here. PdV minus PdV, they cancel, and guess what you're left with? You're left with TdS equals dH minus VdP. Hey, that's the other Gibbs equation. Look at there. We just showed you where the other Gibbs equation came from. And from that Gibbs equation, you can get this equation here. From this Gibbs equation, you can get this equation here. Now let's do that. I don't know if I want to do both of them. I'll leave something for you guys to do, but let's go from here to here and get the equations we need to work a problem. Any comments or questions so far? All right. Well, let me write this Gibbs equation, and then we're going to show you how to get to here. I just need the room, that's all. So we're going to make some room here. You can read all this in your book. You don't really need me. You can read the book. But we're going to come up with some valuable equations that will help us to find heat transfer. And we care about heat transfer. You do like to be warm in the winter, don't you? And you do like to be cool in the summer, don't you? I mean, you have to pay for it. It costs, did you know it costs you money to be warm in the winter, and it costs you money to be cool in the summer? And so if money is important to you, then heat transfer is important to you. Okay, well, we've got our Gibbs equation, and here it is. And let's see, I got lost here. Okay. Gibbs equation. T ds is equal to du plus p dv. Now here's what we're going to do. We're going to divide everything through by t. That's legal. You can divide everything through by t, can't you? And so what you're left with is ds. The t's go bye-bye. And we're going to write this as C sub v. We're going to say we have an ideal gas, like air maybe. If you have an ideal gas, you can write that as C sub v dt over t. If you have an ideal gas, then PV is equal to RT, and P over T is equal to R over V. Can you get from here to here? If you can, we could substitute R over V dV, couldn't we? Yeah. I think yeah. Actually, I think what I'm doing is this bottom one. I was going to do this top one, but I'm doing the bottom one. But we're almost there. What we're going to do is we're going to integrate. Ready? And you know what that is? That's just going to be delta S. It's going to be delta S. Oh, by the way, these are supposed to be little letters too. If you wanted big letters, no, it's no problem, but you'd have to multiply everything here by m. You know how it works. Delta little s is equal to m times delta big S. There you go. But delta little s is equal to C sub v dt over t plus, you could pull out the r, and if this goes from v1 to v2, you could just write natural log of v2 over v1, and you'd be done. You would be done. Now let's do the other one. We got a nice equation here. We just cooked up this equation. See where it came from? We need to use it in an example here in a little bit. Now the other one. Let's do the other one. Here goes. It goes like this. And TDS is equal to DH minus VdP. I think I had that on the board just a minute ago. Yeah, that's right. Now what we're going to do is we're going to divide that by t. That's legal, guys. We can divide everything by t. Do that with me. And what we'll have is we'll have d little s is equal to, now if you have air, let's throw in the idea that you have an ideal gas now. You don't need an ideal gas for that. That's good whether you have an ideal gas or not. But if you have an ideal gas, you could write this as C sub P dt over T. And this here, watch it, if you have an ideal gas, then PV equals RT. And V over T is equal to R over P. Can you get from here to here? Can you make it? Okay. So V over T is equal to R over P dP. So far, so good. Now we're going to integrate everything and see what happens. Here we go. When you integrate, you get delta S. You know, you're going from S1 to S2. And when you integrate, you just get S and you plug in your limits and you have S2 minus S1. That's delta S is equal to C sub P dt over T minus, you could pull the R out, and what you got is the integral of dP over P from P1 to P2. Now that's equal to, you could leave this as it is for right now. But see, that's equal to R times the natural log of P when you plug in P1 to P2. And what you'll get is C sub P dt over T minus R natural log of P2 over P1. I hope I didn't lose anybody, but that's that equation there. That's where it came from. Now we have equations to find the change of entropy. Now, if you have something like water or ammonia, R134A or any of the refrigerants, use the tables. What if you have an ideal gas? You have tables, but what they are is integral tables. I'll try to show you the difference. I was talking about that earlier. But if you don't have saturation tables, is what I'm talking about, vapor dome tables, you won't have vapor dome tables for air or other ideal gases. What do you do then? Well, you use these equations here. That's what you do. Now, I want to talk about this one in particular, this first one here. And I want to show you some wonderful things about it. Then we'll work a problem. How are we doing on time? We're doing okay. We're doing great. Any questions on any of that before we develop this top equation a little bit more for you? Okay, because we need to do some problems and some examples, because this can get pretty boring, this all this algebra stuff. Okay, now here's the one I want to talk about. I showed you where the heck this came from. Here's this lovely equation. Now, if your temperature doesn't change too drastically from T1 to T2, then the specific heat doesn't change too drastically either, and you can pull it out. And so you can pull out constants. You guys all studied calculus, and you know that you can pull out constants. Yeah. So we'll pull it out. Now, the minute you do that, you're decreasing your accuracy a little bit. They've actually integrated these things, and they have a name for them. This whole dang thing here is called S0 in the tables. And actually, this whole thing would be S02 minus S0T1. S0T2 minus S0T1. You'll see those. If you look in the very back of your book, you can just sort of flip pretty much any place back there. Well, not really any place, but there's a whole lot of places that have these little S0s going on back there. Trying to find some here. Yeah, I see some. I see some on table A11. There's some S0 with a little t underneath it there. Those are called ideal gas integrals. And there's a whole bunch more. There's some on table A13, A14, A15, etc. They've integrated those for you. It's more accurate if you use those. But this is not bad. This isn't bad at all, because see, that's equal to C sub P natural log of T2 over T1. And so here's your change in entropy. Now I'm going to talk to you about the second law of thermodynamics, and hopefully I can show you why, if you have an adiabat, this delta S is 0. So you get a 0 equals C sub P natural log. I haven't shown you that yet, but we're fixing to. We'll show it to you here in a little while. But if you have an adiabatic process, the change in specific entropy is going to be 0. It's got to be reversible too. But if you have an adiabatic reversible process, the specific entropy change is 0. And you get this, and from this you can get some wonderful equations. Let me show you those. See if you can get from here to here. Can you make it from here to here? Can you make it? I bet you can. Now we're going to do another little algebra step. We're going to come up here, and I'm going to write this like this. Can you get to here? Can you make it from here to here? Can you make it? I hope you can read my writing. All right, now watch it. We're going to do another algebra step. See if you can get to here. I did kind of a tricky little algebra step there. Can you get to there? It's one of those things they teach you in calculus. we're going to come up with a real nice equation here in just a minute. See if you can get to here with me. Can you get from here to here? Can you make it? We're almost done. We're going to have a wonderful equation. Now, do you remember that R is equal to C sub P minus C sub V? Do you remember that? Like, for example, for air, R is 0.287, C sub P is 0.1004, and C sub V is 0.717. Subtract those and see if I'm lying to you. I'm going to try it, and I'm going to see if that's really true, if I'm just telling you a lie here. Let's see, 1004 minus 0.717. Boy, Jove, that's good, isn't it? In fact, this is good for all ideal gases. There's a relationship. I don't know if I showed you that. I can't remember what I've shown you and what I haven't. But knowing that, we're going to do a couple more steps here. And the next step is T2 over T1 equals P2 over P1 to the C sub P minus C sub V over C sub P. Can you get to there? I bet you can. Now what? Well, I need some room here. We'll sacrifice some of this stuff. Then we need to work a problem. I bet you're getting bored with all this algebra and stuff. They have something called the specific heat ratio. It's a little symbol K. It's equal to C sub P over C sub V. For air, you know what it would be? It would be 1004 divided by 0.717. It turns out to be equal to 0.4 for air. Do that with me. Take 1004, divide by 0.717, and see if you get, and wait a minute, I did something wrong here. I did something wrong. Let me do that again. 1004.717. No, this is wrong. It's 1.4. It's 1.4. Now, if you look in the back here, they have the tables of these specific heat ratios. Let's see if I can find one here. Don't see them. There it is. Air is 1.4. They've got that little K there. This is in table A9 for, I don't know, probably about 50 different gases there. See it? You can look in the back. Like, for instance, helium is 5.193 divided by 3.116, and they said the specific heat ratio is 1.667. And you can look up whatever you want. Okay, now back to this. Let's finish off what we were doing. I need some room though. Okay, so what we got here now is T2 over T1 is equal to P2 over P1 to the, can you see that's 1 minus 1 over K? Because it'd be a 1 minus C sub B over C sub P. Well, that's 1 over K. Because see, K is C sub P over C sub B. And what that is C sub B over C sub P. Or you could write this as P2 over P1 to the K minus 1 over K. We've seen an equation very similar to that. Do you remember? It goes like this. You know what that is? That's a polytropic process. This is an adiabatic process. Guess what? The adiabatic process is a polytropic process. And the polytropic constant is equal to K, which is the specific heat ratio, is the fancy name for it. So we've got some wonderful equations. That's enough theory. Let's do a problem. Do we have any questions?
So
Any
what's the final
question?
equation? What's the final equation there? The two,
Here,
the
let
K
me-
minus 1 over K.
Yeah, let me write it for you. This one's a definite keeper. Now, was that Nathan I just talked to?
Yes, yes.
That's a keeper, Nathan. But now be careful about using that. It only works for an ideal gas adiabat. The equations are nice if you know when they're okay to use. But you can't just go around using equations any old time you feel like it. You have to use them in the right situation, right? Okay, well, here we go. This is problem 650. We're going to do problem 650 now. Let me find it. And we'll have fun doing that. And if we get time, I'd like to talk to you about the second law of thermodynamics. But thank you for your feedback there. I need your feedback. Now we're looking at 650. 3 kilograms of air in a piston cylinder, constant pressure. I'm getting a sense of deja vu. Mohammed, is this what we were doing earlier?
We were just doing that. I asked you about that earlier. This is Nathan.
Yeah, we were doing that earlier. And I drew the PV diagrams, right?
Yes.
Yeah, okay. Well, let's work it to death. Now, you can't use this equation here on it though, because this problem is an isobar. It's not an adiabat. You know they're different. However, we can use those other equations. Let's do that. Now, P1 is 300 kilopascals. T1 is, didn't we add that up and get 300? It's actually 300.15 Kelvin. And we can get, why don't we stop and get V1? I'll shut up for a minute. You guys all know P1 V1 is equal to RT1. So you can get V1 if you know P1 and you know R and you know T1. I want you to get V1 for me. Go ahead. It's air, right? It's air? Yeah, it's air. I wonder if I did that right. Let me go to one of my excellent students here. Reagan, unmute and say hello, Reagan.
Hello.
Hey, Reagan, did you get this V1 for me yet?
Not yet. I
Take your
did
time.
mine a little bit different.
Take your time, Reagan. We know P1 and we know R and we know T1. We should be able to get V1.
Whenever I did mine, I find the T1 and I do the Q and I do the delta S.
Well, that's fine. They didn't ask you to do V1, but I'm asking you. I want you to find V1. Can you get it?
Okay, let me try.
And while Reagan's doing that, I want to get V2. Say P2 V2 is equal to RT2. Now we know P2, if you read the problem, it is, well, we don't know. Yeah, it's a constant pressure, so we know what that is. It's 300. We know P2, we know R, and we know T2. T2 is 500. We know R is 0.287. Back to Reagan. What'd you get for V1, Reagan?
I got 263.
That's not what I got. But when I put in 300 times V1 equals 0.2 times 300.15, I did not get 263. Do it again. P1 V1 equals RT1. What'd you get this time?
Is that 0.287?
Yeah, that's right. 0.2871 cubic meters per kilogram. We got V1, yay. Now we're going to get V2. Now let me go to another excellent student, Nicholas Sabrata. Nicholas.
Hello.
Hello, Nicholas. I want you to plug in P2, R, and T2. We know all that stuff. And I want you to get, what'd you get for V2?
0.478.
Let me see if I got that. Nicholas, not that I don't trust you. Not that I don't trust you. I got 0.478. Good going. 0.4783. How's that, Nicholas? We'll put a 3 right in there. We'll squeeze it in. Yay, we did great. Okay, and now let's do the change in entropy on this thing. I want to show you these equations. Here we go. Now one of them goes like this. We're going to use this equation. Now C sub P, And it's air, right? It's air. So this is 1004. We'll put in our units like we're supposed to. And this is, it's 400, I think, didn't they say? Divided by 300.15.
That's 500 for T2.
Oh, it's 500. Honkin, thank you. Point goes right there. You're absolutely right. And I was absolutely wrong. P2 is, well, they're the same. It's an isobar. Never mind. All of that stuff disappears, doesn't it? It just, do you understand? P2 and P1 are the same on an isobar. Natural log of 1 is 0. And you're done. You are done. So delta S is equal to, do it for me. Let's see. 500 divided by 0.15 times 1.004. Did you get 0.5124 for the change in specific entropy?
Uh-huh.
I like that. I like that. Now you need the units though. Let me pick on somebody here. I don't think I've picked on Brian. Brian, I haven't picked on you all day. Unmute and say hello, please, Brian.
Hello.
Brian, what's the units on this specific entropy? We gotta have the units.
I think it's kilojoules per kilogram.
No,
Oh, no.
you're right about the kilojoules per kilogram, but you're missing something, Brian. What are you missing?
Let me take a look real quick.
Brian's trying to figure out the units for the change in specific entropy. We've got to know the units on this stuff.
It'll be times would it be kilograms times temperature? Or
Yeah, you need the
Kelvin?
Kelvin here, Brian.
Okay.
Good going. I'll pick on somebody else here in a minute. Now, there's another equation that I was trying to show you guys, and it goes like this. We're going to see if this works. Now, we know all this stuff. We know what C sub V is. It's 0.717 kilojoules per kilogram Kelvin. We know what T2 is, thanks to my helpful student, it's 500. T1 is 300.15. We know what R is, it's 287. And we know what V2 is. It's 0.4783. I forget which wonderful student helped me on that. And we know what V1 is. It's 0.2871. Now I want you guys to plug in this equation. Can you all see that equation? Does it show up okay? Barely. I think it barely shows up, yeah. Plug in all those numbers and tell me what you get. Go for it. Well, I did all that and I got an answer. I got 0.5124. Of course, the units are kilojoules, kilogram Kelvin. Did anybody out there get that same answer?
Uh-huh.
Yep.
Good. Hey, well, because look, we already did it. We already did it a different way. I'm just trying to show you that these equations give you the same answer. I showed you where those equations came from. They give you the same answer. That's the change in specific entropy. That was good that we did that. I need to tell you about the second law now. Do you have any other thing that's bothering you or questions about anything? Otherwise, we're going to talk about the second law of thermodynamics. Well, okay. I'm going to erase all this stuff. I hope you got that 0.5124 because we know it's right because we did it the other way. We did it two different ways, didn't we? And earlier, for one of my excellent students, I drew the PV and TS diagrams. All right. Well, let's talk about the second law. Now, we talked about the Clausius inequality. We talked about the Clausius inequality. And if I can remember how that goes, it's for a cycle. They call that the Clausius inequality. And it was just developed by experimental means when Clausius studied steam engines, dozens of them, I don't know, maybe hundreds of them. But see, you can break this into two parts. If you break it into this part here for a cycle, that little circle means cycle. You can either get 0 or you'll get this here. It's either going to equal 0 or it's going to be less than 0. Now, this is what you get if you have a perfect engine with no friction and no irreversibilities. This would be the reversible cycle. This is the irreversible cycle. And we've been plotting cycles. We did a Carnot cycle, which would be one of these. A Carnot cycle is reversible. And I showed you that this integral around the whole cycle is 0 for that Carnot cycle. I showed you that. But today's topic is what happens if you have an irreversible cycle? And this is all in your book. Let me show you the page. And we'll have our second law. If I can find it here. It's on page. Yeah, it's on page 191. I'm looking at page 191. If this doesn't make a whole lot of sense to you, don't worry. At least you'll have some idea where in the heck the second law came from. It came from this. What they did was they plotted up some cycles like on a PV graph. This could be a PV graph. And here's a process going from state 1 to state 2 on a reversible process. And then they came back, they call this process A, and then they came back from state 2 back to state 1. They made a cycle, and it's reversible also, and they called that process B. And then they wrote the cycle. They're talking about this here because it's everything's reversible. So you'll get from 1 to 2, dq over t, plus from 2 to 1, dq over t will give you 0 for that cycle because it's reversible. All processes are reversible, and for a reversible cycle, this thing is 0. Remember, the definition of entropy comes from this fact. In fact, if you remember, the definition of entropy is given by that equation right there. It's a definition. Okay, and then what they did was they went a different route. They went from 1 to 2 on this irreversible process. They call this process C, and it's irreversible. You'll discover from now on, when we have an irreversible process, we use a dashed line. Reversible processes are solid lines. Irreversible processes are dashed lines. Now, if you wrote this cycle, go from 1 to 2 on the irreversible process. Let's label that process C. We'll label this process A and this process B. Go up process C to 2, and then come back from 2 to 1 on process B. We'll come back on process B. That'll work. We want to come back on B or A. Let me think a minute now, just a minute. Go up on C and come back on, yeah, let's come back on B. We'll go up C and then we'll come back on B. But see, there's irreversibilities in that cycle. And so you don't get 0, it's less than 0. See, for a cycle that has irreversibilities, see, this is what you have if everything is reversible. But if there are any irreversibilities, it's less than 0. So it's less than 0. Now we're going to do a little algebra trick. We're going to subtract this, all of this from that. Now, when you do that, algebra students, here's what you'll get. So far, so good, I hope. Then you take that, you subtract that. Now, when you take that and you subtract that, those are both the same. They go bye-bye. Now here, what you have is a 0, and you're subtracting something that's less than 0. Now, when you subtract something that's less than 0, guess what? The sign changes, and it's bigger than 0, isn't it? It's bigger than 0. Okay. Well, they don't want something bigger than 0. Hey, you know what? We're right at the bottom of page 191. If you go to page 191, I think we're pretty much there. Okay, so let's see what we got here. This here, by definition, is the change in entropy from 1 to 2. the change in entropy from 1 to 2. And what they decided to do is they decided to set that equal to this value here, put it over on the right. And add something to it. Whatever it is, it's going to be a positive quantity. It'll be a positive quantity. See, if 5 minus 3 is greater than 0, and you wanted an equal sign, well, you could put the 3 there, but you'd have to add 2. Whatever you're going to do, you're going to have to add a positive quantity. They decided to call this the entropy generation. So the change in entropy between 1 and 2 is equal to this. But see, the change in entropy between 1 and 2 is the same no matter what process you take, because entropy is a property. It's like temperature. The temperature between 1 and 2 doesn't matter which path you take. It's the same change in temperature. The pressure between 1 and 2 doesn't matter which path you take. It's the same pressure. Even if you take this irreversible process, the pressure between 1 and 2 is the same change in pressure between 1 and 2, no matter what the process is. And so the change in entropy between 1 and 2 is, you could put an A here, it wouldn't matter. Or you could put a B, or you could put a C, it doesn't matter. They're all the change in entropy will be the same, but no, you have to leave that C there. But here's your second law. Turn the page there, and there it is on page 193. Let me write it out for you. Oh gee. You might want to read this so it'll make sense to you. But on page 193 is your second law, the second law of thermodynamics, and it goes like this. They write it like this. They decided to call this your generated entropy. Now, they wrote it with big letters. If you wanted little letters, you'd go little s2 minus little s1. I call that delta S. That's what it means. Final minus initial is the heat transfer amount between 1 and 2 divided by the Kelvin or Rankine temperature at which that heat transfer takes place, plus the generated specific entropy. You can put a 1 and 2 in there if you like. They call that generated specific entropy. We now have our second law of thermodynamics. Actually, they gave you the second law before. We kind of skipped over it. Let me go back over that. We have 5 minutes. Go back to page where is that? It's in chapter 5, I think. Yeah. The second law of thermodynamics, it kind of snuck it in on us, but it's on page 149. Let me make some room here, and then we'll write it. The second law, but see, this is written in an English sentence. There are two versions. There's the Kelvin-Planck version, and there's the Clausius version. Of the second law, but it's written in an English sentence. The Kelvin-Planck version says, if you have a heat engine it's got to have some waste heat. What they're saying is you can't have a heat engine like this with no waste heat. See, here's the high temperature. And what they have is you're getting work here, but you don't have any waste heat. It's impossible. It's impossible. I'm reading it for you. I'm on page 149. It's impossible to have a heat engine with no heat sink. See, this is a heat sink. You don't have any. It's impossible to construct a device that will operate in a cycle and produce no effect other than the raising of a weight and the exchange of heat with a single reservoir. See, here's our single reservoir. See, if you had that, you'd have 100% efficiency. Because whatever this QH was, the efficiency would be the W over the QH, and they would have to be the same. Whatever the energy transfer going in would have to equal the energy transfer going out, because there's no heat sink, and you would have a 100% efficient heat engine. They don't have such a thing. Heat engines have a heat sink. They have this heat transfer out at a lower temperature, and you can't have that. That's a second law written in an English sentence. Now, the second law written in symbols, here it is. This is the second law written with algebraic symbols. There's also a Clausius version on page 149. And what it deals with is a refrigeration cycle. You all know they go counterclockwise. Everything is just the opposite. They have a high temperature. They have a low temperature. The Clausius version has a refrigerator, but you don't need a heat or a power input. We all know that you have to have a W or a W dot input for your refrigerator. You got to plug it in. What they've got is a refrigeration cycle with no external power source that you have to plug in. That's impossible. It says so. Read it. The Clausius statement on page 149. It's impossible to construct a device that operates in a cycle, produces no effect other than the transfer of heat from a colder body to a warmer body. I'm sorry, but heat doesn't transfer that way without costing you something. If you want to transfer heat from your cold hot dogs to your hot kitchen, you can do it, but you're going to have to pay the electric bill. Well, I don't know if any of that made a lick of sense, but I gave you a huge dose of theory today. And I will try to give you more problems and work problems next time, but it's sad. Our time is up.
I have a question, Professor.
Go ahead.
On the homework, I mean 50. Whenever I read the question, you just ask for the TS diagram. So now,
I want the PV and TS diagram.
okay, because it
Please.
was not. You
Yeah.
didn't mention that on the writing.
Yeah,
so
I didn't explain that very good, but
can I email
everybody
you
do both. Everybody do both, PV and TS.
Yes, I'm saying, can I email, because I already submit. The first one I submit was I didn't put the PV diagram. Can I email you the second homework?
Oh yeah, you can.
Okay, I'll email you that.
I might be kind to everybody on this, because you're not used to that yet.
Because
Don't worry about that. Don't worry about that. But what I want is I want PV and TS for a while.
Yeah, I email you.
Anybody else? Well, I got to go. Bye-bye, everybody. I'll see you Tuesday at 9 or 11 o'clock. Tuesday 11, right?
Have a good day,
Sounds
Mr.
good.
Griffin.
Bye-bye for now. So
Thank you.
long. Thank you.